this kinetics video, we are going to look at Michaelis-Menten kinetics with two types of inhibition. First, we're going to look at competitive inhibition, and then we're going to look at non-competitive inhibition. So competitive inhibition is when another substrate mimic will compete with the substrate. So if you recall in the previous video when we looked at the straightforward basic Michaelis-Menten kinetics, we had something like this. We had a declaration, I think I called it, where we said that the total enzyme concentration, ET, is equal to the free enzyme plus the loaded enzyme. Well, now we've got the addition of an inhibited enzyme. So this is inhibited enzyme. So it's an enzyme that's loaded with some kind of competitive inhibitor. So this is the add-on here. And this add-on leads to consequences that we're going to flesh out right now. Okay, so we saw in the previous video, again, when we looked at Michaelis-Menten kinetics, that we had an expression like this on the left, where we had the substrate, the transient loaded enzyme concentration, ES, shown here, is equal to the free enzyme, E, multiplied by the substrate concentration, S, divided by the Michaelis-Menten constant, Km. We can come up with a similar expression for the inhibited enzyme, EI, where we just replace the substrate concentration S with the inhibitor concentration I, and we replace the Michaelis-Menten constant Km with an equilibrium constant for the inhibitor, Ki. Okay, so we have a similar expression. Let's clear the annotations. Okay. So then we're just going to do some algebra, and we're going to manipulate the equation. Ultimately, the goal is going to be the same. We need to isolate an expression for ES. Why? Because ES is a transient species. It's produced and consumed, and therefore we can't measure it accurately, and we need to know it accurately because it's in the rate expression. Okay, so we're going to massage this equation algebraically to solve for ES. So in doing that, let's look at this equation in the box, which is going to be pivotal to what comes next. So we have, if you look on the left-hand side here, we have basically this top expression here, ET is E plus ES plus EI. And we take this expression that I'm highlighting here, and we solve for E, and we insert it here. So Km ES over S is just equal to the enzyme, the free enzyme concentration E. We have the ES, we keep that there because we want ES. And then we take this expression here and we solve for EI by just putting it in here. Now, we notice that this equation in the box here, every term has an ES in it, which is what we want because we're going to factor out the ES. Okay, and if it wasn't clear, which it might not be clear unless you really look at this, the extra material here is because this expression for EI has an E in it, and we just pack in this material for E back into this expression. And if you take a look at that for a second, you'll see that that's what happened. Okay, so then moving on, we have our expression for EI is here. We've just rewritten that. And then we factor out all these expressions for ES, and then we rewrite. We've actually got an ES. We factored out ES over S. So if we look at this carefully, we've got ET, or the total enzyme concentration, is ES over S multiplied by Km. That returns this term here. Then we multiply it by S. Well, the S's cancel, so we're left with just ES, which gives us this term. And then we multiply it by this material, KMI over KI, and we return this term here. So this equation, this setup here, is just the same as the boxed equation, but we factored out ES over S. Then we cross multiply to isolate ES. So we multiply both sides by S. We divide both sides by the expression in the brackets here, and we get this expression. We've also dragged Km and S outside of the bracket. And we do that, basically it's stylistic. You'll see in a second, we're gonna return an equation that looks similar to the original non-impeded Michaelis-Menten expression. But here we've just dragged S and Km back outside the bracket, and we're now left with this term 1 plus I over Ki. We are reminded that the overall rate that we're interested in, the rate determining step, remember from the previous video where we looked at the basic Michaelis-Menten rate, is KBES. Okay, so we have now our transient species ES that we can now solve for and plug back into the rate expression. So instead of writing KBES, we have KB and then all of this stuff. And we are reminded that we can assume that KBET is equal to Vmax. So this, again, was in the previous video. So recall that KBET is equal to Vmax. So we've got KB and ET here. That multiplied by S, that just becomes Vmax multiplied by S. And so we have our final expression. The rate of formation of product is Vmax S over Km, and then we have this bracket 1 plus I, the inhibitor, over Ki, the inhibitor constant, plus S. So it looks like the role of the competitive inhibitor here is to modify the Michaelis-Menten constant. Compare it with the original Michaelis-Menten expression. So I'll add it here just in case you don't have access to it immediately. Just as a comparison, I do have a summary slide in a second, but let's just compare it on the slide while we have it. So compare it with Vmax S over Km plus S. So we can see a competitive inhibitor just has this extra term that affects the Michaelis-Menten constant, and that's it. So that's pretty important. So let's have a look at the consequences of that. We do want to do something similar. We want to get a Lineweaver-Burke plot of this form of the Michaelis-Menten expression. So we do the same procedures we did in the previous video. We divide all terms in the expression by S, and then we invert the expression and we get a y is mx plus b type equation. So you can see here, we've taken our expression, we've divided all terms by S to simplify the expression. We take the inverse exactly as we've done before, and then we get this y is mx plus b form of the expression. And you'll notice by comparing it with the non-competitive inhibition form that the only difference is we've got this extra term here, this bracket term here. Otherwise, it's identical to before. We get a y is mx plus b plot. We can plot it on a spreadsheet, and we could get access to the Michaelis-Menten constant and all the other variables as before. The one other thing is we'll notice that if we increase the concentration of the inhibitor, we effectively make the slope of our curve steeper. And we can see that here Hopefully that had become straightforward, because if I just annotate over this, if I just superimpose this, we've got 1 over V is 1 over V max plus Km. And then we've got this add-on 1 plus the inhibitor concentration over the constant with the inhibitor, all over Vmax, and then multiplied by 1 over the substrate concentration. So this is the expression that gave us the straight line form. And we're saying that as we increase the inhibitor concentration, the slope increases. Well, let's remind each other what the slope was. The slope is going to be this. This is our slope. And you can see that the slope is proportional to I. So obviously, as you increase the concentration of I, you increase the slope. Okay. So having emphasized that, let's continue. Okay, now let's contrast that with non-competitive inhibition. So non-competitive inhibition is where there's a chemical I that doesn't directly compete with the active site of the enzyme. It competes at a non-active site, an alternative site, to indirectly affect the active site. So let's look at how this impacts what we're talking about. So to emphasize what was done previously, so previously with no inhibition whatsoever, we just had this declaration. Total enzyme is the free enzyme plus the loaded enzyme. But now we've got an inhibited enzyme. Rather than direct inhibition, so we've just had EI, now I've written the I to the left side of E to represent the fact that it's not the active site. So we can inhibit both of these guys. We can inhibit the free enzyme to give IE. We can inhibit the loaded enzyme to give IES. We didn't have a term like this previously in the competitive inhibition because the loaded enzyme would already prevent the inhibitor from docking with the enzyme. But the fact that we're docking off-site, a non-active part of the enzyme, means that we can have this extra term. So because of the presence of these extra terms, we're going to have something different in the Michaelis-Menten expression. Okay, so having pointed that out, let's have a look at what we're going to do with it. Okay, so same as before, we have our original expression for ES, our transient species, which we've seen twice already now. We have an analogous equation for IE, where we replace the substrate with I, the inhibitor I, and we replace the Michaelis-Menten constant with the inhibitor version, Ki. And then we have a similar expression for the loaded enzyme and inhibited species, which is analogous to the other two expressions. Again, the goal is going to be to come up with an expression for ES. That's the long-term goal. So we know that from our top equation here, we know the total enzyme is E plus ES plus IE plus IES. And then we just solve for E, we solve for IE, and we solve for IES. So just some basic algebraic manipulation. I've got arrows going everywhere here to remind my students where these things are coming from. We substitute in E here, and again, essentially it's just some basic algebra, but we end up, again, similar to a few moments ago, we factor out ES over S, and we have this long expression here. So you can pause the video, have a look at it. It's pretty straightforward where that comes from, although it might take a couple of seconds to see it. But we have this expression here. And then again, we've taken the Km and the S outside of the bracket to return the similar parenthesis that we saw in the competitive inhibition example, which is 1 plus I over Ki. Then we solve for ES. So we isolate ES and we have this expression, which again has this familiar bracket, this 1 plus I over Ki. Now, the loaded enzyme that's inhibited is not active. That goes without saying. That's the whole concept of inhibition. So the rate determining step is still the same KBES. So if we look now at the Michaelis-Menten expression with indirect inhibition or non-competitive inhibition, we have this here. So I could rewrite this as, remember KBET is Vmax. We've got Vmax S over S plus Km. And then you can see, before I finish writing this, that the bracket 1 plus I over Ki, it not only affects Km, but now it also affects S. So the role of this inhibitor, this non-competitive inhibitor, non-competitive, is not only to modify Km, but also to modify the input of the substrate. So let's see, I think I have a summary. I think I show you a straight line plot and then a summary of everything so we can put them side by side, which is always useful. So let's get this non-competitive inhibited form of the Michaelis-Menten expression into a Lineweaver-Burke format, a straight line expression. And without going through the rigmarole of doing this, you can probably predict already we've got this extra term here that's going to impact S. So previously we just had this term here, but now we've got this term over here. We can still get a straight line expression. We can still do all the usual plotting on a spreadsheet. And we can solve for the Michaelis-Menten, the adapted form of the Michaelis-Menten constant here. We can solve for the maximum rate, etc., in the presence of the inhibitor. So none of this is new, so I'll blast through that a bit. But let's look at the effect of increasing the concentration. Notice we don't pivot on the y-axis at x equals 0. We have unique values now. So this is a slightly different profile when we look at multiple plots in the Lineweaver-Burke form. And we can actually therefore use the Lineweaver-Burke form of this expression to decipher whether we have competitive inhibition or non-competitive inhibition. So you have an inhibitor, you don't know how it affects the enzyme. You can vary the concentration of substrate, vary the concentration of inhibitor, plot it in the Lineweaver-Burke form, and you can see whether it pivots on the y-axis or whether it doesn't, and you can see that in this summary. So if I can maybe make this a little bit smaller to see everything at once. Yeah, that might be a bit better. Okay. So let's just look at the competitive versus non-competitive inhibition first. So you can see the two equations here. These are just in the regular Michaelis-Menten expression. Numerators are the same. Vmax multiplied by substrate concentration S. Competitive inhibition, the extra material, the 1 plus I over Ki, only affects Km. Whereas in the non-competitive inhibition case, the 1 plus I over Ki affects not only Km but S as well. And we get this pivoting around 1 over Vmax on the y-axis, where x is 0 for the competitive inhibition, whereas we get unique values here. So basically, the inhibitor can affect Vmax. Let's now compare this. So now we've seen the differences between these two types of inhibition. Let's compare it with the natant original version, which lacked that term 1 plus I over Ki in the denominator here. So this is a nice summary of all the types that, there are more types of inhibition, but these are the types that we'll look at in my course at least. Okay, let's look at a question. A Michaelis-Menten question with inhibition. So it reads, the following data were obtained for an enzyme in the absence of an inhibitor and in the presence of an inhibitor. And specifically, we're told it was competitive inhibition here. So we have some data. It looks like it's in units of micromole per second, and the substrate concentration is in millimole. It asks us to draw a Lineweaver-Burke plot of the reaction kinetics, label the axes, and provide points where each line crosses the axes. So because it's competitive inhibition, you'd expect this pivot point here with a constant Vmax. So you wouldn't hand draw this by any means, you'd plot it on a spreadsheet, but we do that. And we can confirm indeed that it's competitive inhibition because of this pivot point with a fixed Vmax. Okay, so it's definitely worthwhile trying to plot some of this data on a spreadsheet. Again, I've just written Km here, but remember that it's this adapted form of Km. Okay, and that actually is the last slide in this particular video. So I will stop the video right there.